So in this video, all we're going to do is go over another sorting algorithm, but this time we're going over something a little bit more in depth. This is a recursive sorting algorithm. So there's a little bit more to do. It's more involved, there's more pieces to the puzzle and more steps. There's also a lot more complication involved. So just take your time, pause the video if you need to, go back, rewind, and watch it again. Slow it down to whatever pace you need to, okay? So what we're looking at is something called the merge sort, and this is a very popular recursive sorting algorithm. It's definitely not the most popular. I would say that's probably the quick sort. There's a few others out there as well, but we're going to look at the merge sort because it's the most clearly defined and easiest to understand when it comes to a recursive sorting algorithm. So merge sort uses that classic method of problem solving we've come to know as the divide and conquer strategy. And what that basically means is we divide up our data, we divide up our large problem into smaller, more easily solved problems. And then once we've solved those small ones, we combine it all back up together to get a final solution to the original problem. Does that sound familiar to you? It should. That's almost the exact definition of recursion, which is why, of course, we use recursion when we implement the merge sort algorithm. So, how does this whole process work? Well, let's assume that we're given an array of size n. We don't know how big that is, and it doesn't matter. We're just given an array of size n. The first step, according to our divide and conquer strategy, is to divide it in half. Now, not all divide and conquer strategies divide exactly in half, but this one definitely does. So, we're going to divide our array in half. So how do we find the half? Where do we find the midpoint? Well, we take the left index, we add it to the right index, and we divide by 2. It's like it's the exact same way you find the midpoint of a line, right? You take the left point, you add it to the right point, and you divide it by 2, and there you go. Now, why did I say left index and right index? Why didn't I just say the index 0 and length minus 1 divided by 2? Well, the reason being is there's more than one strategy when we go about this. Some people will actually create brand new arrays that are exactly equal to half of the current array. So you're going to have a left half and a right half, and that's perfectly fine. But it means you're doubling your data every step, basically. So you're creating two brand new arrays, even though that first array is still sitting there in memory. So you got to keep that in mind. The other strategy is instead of creating two brand new arrays, what you do is you maintain the same array the whole time, but the way you divide it up, quote unquote dividing up, is really just calculating where the minimum and maximum index are that you're currently looking at. So if I divide a full array into half, that means the left half has all the index values from 0 up to the midpoint. The right half has all the index points from the midpoint to the end. So it's up to you to decide which strategy works for you and which one you're more comfortable with. But you just got to make sure that the parameters make sense for the algorithm that you're trying to actually solve. So how do we find the midpoint? Left plus right divided by 2. So that's the divide step. Now, once we figure out how to do that, we have to recurse. We're going to continue to divide and divide and divide. We're dividing in halves into halves into halves into halves. And then we're going to sort each division. Eventually, we're going to be left with, once we've divided it so much, we're going to be left with either 1 or 0 elements. That's our base case. If we have 1 or 0 elements, by definition, that's already sorted. So therefore, we can return our sorted set up the recursion. Well, once we return that back up, the next step of the algorithm is to merge our already sorted halves. Okay. So we're going to rebuild the final array by combining or merging the divisions, the sorted divisions, I should say. So each merge step basically returns an array the size of both of the partial arrays combined. So if the first array has 3 elements and the second array has 3 elements, then my return array is going to have 6 elements. If my first array has 3 elements, the second one has 4 elements, my return array is going to have 7 elements. Now, how do we actually merge? Well, we look at our 2 partial arrays, we grab the lowest element out of the 2 arrays, and we stick it in our return array. That's our first element. Now we're going to repeat that process, continually grabbing the next lowest element between the two partial arrays and putting it in the next slot of the return array. When we're all done, we know we're done because the return array is full, in which case we don't have any more to do. So that's going to return back up the chain. Pro tip, this algorithm is typically done with two subprograms, a divide and a merge. Now that's not necessarily what they're called, but that's basically how it breaks down. Let's take a look at an example of this in live form. I'm going to pause the video for a second. Okay, so come on, reset. Maybe. All right, so here we go. So we have this, now we actually have the data start over. So we have our completely mixed up array, and you can see it dividing in half, and dividing in half, and dividing in half, and now we're left with 8 one-element arrays. Now we got to merge everything back together. So it takes the lowest element of the two arrays and combines them. Takes the lowest element, two of the arrays, combines them. We're building up a combined array of both of those elements, and you're going to see in the next phase, it's then going to combine two of the two-element arrays together to make a 4-element array. So it compares the 1 and the 5, it takes the 1. It compares the 5 and the 3, it takes the 3. Then the 5, and then the 6. And the same process is going to happen on the other side. Again, it's always taking the smallest element to do the merge. It doesn't necessarily always have to come from the same array, though. And yes, of course, there are shortcuts you can take. It's up to you to decide whether you want to take those shortcuts or not. Now, in all recursion, if you start making special cases, the elegancy of that recursion usually breaks down, and then it's not such a pretty solution anymore. It may be a little bit more efficient, though, so it's a balancing act. So we see here, after all is said and done, we have a completely merged and sorted array. 1, 2, 3, 4, 5, 6, 7, 8. So let's actually look at something a little bit more clear. Now here we have an array of 8 elements again. It doesn't always have to be an even number. Sometimes it's going to be an odd number. In fact, when it's an odd number, it's usually easier to find that midpoint in terms of how we divide things up. We just have to realize, are we rounding up or are we rounding down? Well, if you're always working with integers, which we are because we're talking about index values, then the integer truncates, and which means it's always rounding down, basically. So if you have 9 elements, the midpoint is going to be, let's say 0 plus 9 divided by 2. That's going to be the midpoint is going to be index 4. Okay, so let's take a look at this. So I've even written the recursion levels on the side here, and you can see that it goes 0, 1, 2, 3, and then it starts counting back up. So we can see the call stack builds up to the third stack, and then it starts popping items off that call stack to get back to our original call to the sort algorithm. So the first thing you're going to see is the division step. We're going to divide. So cut it in half, cut it in half, cut it in half, and now we're at a point where everything has one element. And the merge step looks at the two halves. So for example, 52 and 24, it's going to combine these two. It's going to take the lowest two of these and say, well, 24 comes first, then 52. Then it goes on to the next set, 63 and 45. Okay, 45 first, then 63. Then the next set, 17 and 31. 17 first, 31 next. And then 96 and 50, we get 50 and 96. And then the step after that is going to combine the two sets of two arrays. So we see how it all builds up. And it's actually a pretty quick process. It's just always taking the lowest one to build up that next set. And then all of a sudden, we are done. We have the entire merged array. Now, it seems like a very straightforward algorithm, and it really is. But it can be tricky to implement. I think it's probably more tricky to implement a good merge than it is a good divide, because divide is just a matter of finding that midpoint and then breaking it up, depending on whether you're creating new arrays or whether you're breaking it up based on index values. It's up to you. So what about the time complexity of this thing? How efficient is this? Well, in terms of memory, normally the normal implementation of this is going to be big O of n, which means it's going to take you an extra equivalent size of the original array to actually handle this. And that makes sense, especially if you're making those duplicate or those secondary smaller arrays. All right. Now, we said that the merge sort is really made up of two parts computationally. It's made up of those two pieces, the divide and then the merge. So what does it cost for each? And then we're going to combine them together. So let's see what the division cost is. Let's think about this. In this phase, the array is basically divided in half until there is only 1 or 0 elements. Now in the example that we saw, we had exactly 8 elements in that array. Well, how many divisions did it take us to actually get to 1 element? Well, it took 3 divisions. So we had 8 divided by 2, 8 times 1/2 gave us 4. 4 times 1/2 gave us 2. 2 times 1/2 gave us 1. So it took 3 steps. Well, let's simplify this, all right? We're going to put these together, and we're going to put it in terms of the number of elements n and the number of divisions y. So in this formula that we see here, our calculation is 8 times 1/2 cubed, because we multiplied by 1/2 3 times. And that ended up with a value of 1. Now, if we simplify this, if we just think in terms of n, which is the number of elements, and y, which is the number of divisions, how can we simplify this entire equation? Well, first of all, let's write it out the way we see it. Now, hopefully if you can figure out how this breaks down. Now, depending on which classes you've taken in math at the high school level so far, this may be a little bit easier for some than others. So if you've taken advanced functions, you should probably be fine with this. So what are we looking at here? Well, the first thing we need to do is we need to simplify this, which means we need to get that y into that fraction. So if we factor that exponent through, we end up with something like this. N times 1 over 2 to the y equals 1. We multiply that n through, now we have n over 2 to the y equals 1. Well, now if we multiply both sides by 2 to the y, we get rid of that fraction. So we have 2 to the y times n. 2 to the y, which cancel out, which means we only have n on the left. And the right side is 1 times 2 to the y. So we end up with n is equal to 2 to the y. That's a much simpler equation. Not only that, that's actually a pretty special relationship. It's what we call an inverse exponential relationship. And it has a base of 2. This is a very special form of expression. We can actually rewrite this as something called a log. Now, if you've never covered logs before, don't worry about that. Just accept it for what it is for now, and we can go into more detail on it later. But basically, that n is equal to 2 to the y can be rewritten as log base 2 of n. So what's the final cost of dividing? Well, it's log n, where the logarithm is a base 2, not a base 10. Now this is something that some of you are not used to, because normally in math class we're always working in base 10. But there is a way to deal with that. All right. If you don't know what a log is, basic definition. It's a quantity representing a power to which a fixed number, which is the base, must be raised to produce a given number. That's a lot of technical jargon. Think of it just as an inverse exponent. That's the easiest way to look at it. It's an inverse exponent. That's the way I always think about it. So we know our first step, the divide step, is log n. But what about the merge step? We're putting it back together. What does that cost? Well, it's actually pretty cheap. So the merge step is simply grabbing the next smallest item every single time, which means we're only looking at all the elements. So what that means is it breaks down into just simply a cost of n. We need to look at each element at least once. That's cheap. But how does that actually factor into the equation? What does that actually mean? Well, since the merge actually has to happen for every single division by 2, that means that we're doing a little bit more work than we thought. So what happens is this relationship becomes a product. So remember, we're doing the merge for every division by 2. Well, the division by 2 was log n. So if we're doing the merge for each one of those, that means it's n times log n. So our final expression, our final big O notation, time complexity, is big O of n times log n. That's not bad. If you think about what we did last time, we were looking at n squared. And those algorithms were taking hundreds of millions of operations. So the example if we take it like this, let's do some simple math here. Where's my pencil? Here we go. If we have an input size n of 10,000, so if, oops, back up that train. There we go. If we have an input size n of 10,000, so if n is equal to 10,000, which is fairly reasonable, both of those iterative sorts that we saw before, the insertion sort and the bubble sort, they were both big O of n squared. So that means their cost is equal to 10,000 squared. Well, I think that's 100 million. I believe that's 100 million. Yeah, so this actually comes out to be 100 million. So that means in order to do the sort on 10,000 items, it takes 100 million operations to solve that problem. Oh my goodness. So let's look at the difference for n log n. When we do n is equal to 10,000 for n log n, this is actually a significantly cheaper operation. So 100 million for n squared. But for n log n, let me go back to my pen here. There we go. So if n is equal to 10,000 and we're dealing with n log n, it actually only takes 132,000 operations. So 100 million versus 132,000, that's a huge significant difference. And the best part about that is that it actually gets more efficient as n grows. So, because n squared is growing a lot faster than n log n, which means the more that we have, the better results we end up seeing. That also means the inverse relationship. The less we have, the less impressive it is. Which is why we saw things like that insertion sort actually beat the merge sort and the quick sort when the data was pretty much already sorted. So we get into those weird relationships where it's not always the best idea to use what's quote unquote the most efficient algorithm. We have to look at more than just that efficiency. We have to look at the implementation of it. We have to look at what our data set looks like. There's a lot more involved. So how do we calculate that log base 2? If you've never done this before, we use something called the change of base method. And it's pretty straightforward. I can show you real quick. Let me just pull up my pen here. Here's my pen. So if I'm trying to calculate something like, I want to calculate the log of base 2 to the, or sorry, the log of, let's say, 10 to the base 2. This can be rewritten in the form of log base 10. And the question is, what goes in which one? So the base goes down here, and the 10 goes up here. So when you do this work, you're actually going to be able to come up with a result. Now, I can pull up my calculator real quick here. So if we're going over here, you can see this now. Let me just clear this calculator. So if we take 10 log, and we divide that by 2 log, we end up with a value of 3.32. Now, that's why, or that's how you end up calculating that 10 to the log base 2. All right, now that's obviously not going to be something that you're going to be commonly doing. You don't really necessarily need to do it. But it's something you need to understand just in case you're really looking at the math behind all this. So how do we implement this function? What's the work behind it? Well, first of all, we need to realize that we really should break this up into 2 steps, the divide and the merge. So when you create this function, you're going to create a function called merge sort. That merge sort function is your divide step. That step is where you're going to be finding that midpoint and breaking it up into two equal parts. So, So as such, you may have an initial subprogram called merge sort, which takes the array as a parameter and returns a sorted version of the array. But there's a little bit more to it. This is the divide step. My computer's not going here. There we go. So the merge sort is the recursive subprogram. So you're going to be calling that merge sort within merge sort. You're going to divide the problem into half each step by merge sorting each half. So you're going to merge sort the left half and merge sort the right half. There's your recursion. But where does the merge come in? Well, I'm glad you asked. What is going on with my thing here? So the final step is that merge step. When the two halves have actually been divided, they're going to need to be merged back together. So the merge result array is returned back up the recursive chain. So as we pop things off the stack, it gets sent back to whatever called it. Somewhere in your code, you're going to have this statement: merge of the merge sort on the left side of the array of the merge sort on the right side of the array. Somewhere in your program, you are going to have this line of code where the left part of the array and the right part of the array is how you break it up. Okay? I'm not going to tell you how to do that. That's going to be up to you. But that, in essence, is your algorithm. So we divide, and then we build it back up. And the recursion, you can see right here, we're recursing on merge sort. This is the tough part. Okay, we're going to leave it there so you can actually try the implementation of this. Take your time and do it separately. You have do your merge and do your division as two separate entities. It is possible to do it as one subprogram. I don't actually recommend that because you're going to find that it's a lot more complicated and prone to error if you do so. So let's move on and give it a go.